We'll move on now to water pumps. So there's many varieties of water pumps on the market. I don't know, varieties, types, whatever you want to say. There's high head pumps. So again, they pump really high. You need to pump 500 feet up to the top of a building to run emergency water for fires in an apartment building, okay? So there's high head pumps out there for really high head applications. Medium head pumps, low head pumps, you get it, okay? So depending on how high and how much force we need and what the flow rate is, we've got different pumps for those applications. The more head pressure means the more energy it takes to overcome. As it's pumping up, well, water weighs, it weighs something. So the higher you're pumping, the more weight in that pump, in that pipe, and the more pressure that pump has to overcome. You never size a pump based off of the horsepower, okay? We'll just throw that out there right now. Because there's so many different types of pumps, you could get one horsepower pump that does 100 gallons per minute, and you can get another 1 horsepower pump that does 10 gallons per minute. And they'll just be at different head heights, and it also depends on the specifications inside that pump, how well it was machined, how close the tolerances are, and how efficient it is. So never size by just off of horsepower alone. Always size a pump based on the flow rate that is required at your specific head height, okay? So at a specific pressure. So the steps to doing this: first, we need to figure out what flow rate is required. And we do that through some of the calculations that we've already covered earlier on in some of our earlier sessions for the fish and culture tank design. So we figure out the flow rate required. Next, we need to figure out the friction losses through the pipe and through all of the fittings that we're using, okay? How much friction are they creating, and what potential are they taking away from our water pump? The total dynamic head, TDH pressure, so what's our total dynamic head pressure? Taking into account all of our friction losses through pipes, fittings, and vertical distances, everything. And is the water pump self-priming or not? So does the water pump pull vertically from your low point? Let's say you have a pump here and you have the point where it's sucking from, the sump, 4 feet below. Will it suck the water up to the point of the pump and then push it on further to wherever you're sending it? Or does it already need to have water in that impeller to actually make the water move? That's the difference. A self-priming will suck the water automatically up a given distance. It'll be in the specifications, and it will push it to the delivered target. So like a jacuzzi water pump, 10 feet of self-priming head pressure. It will tell you right on the specifics. It'll pull water up 10 feet to the pump and then push it wherever you need it. The pumps I use here are low head centrifugal pumps, and they are not self-priming pumps. So for that, if you don't have a self-priming pump, you will need a check valve, which is a one-way valve, and a pump trap on the inlet side to keep that pump flooded. Which means, okay, a one-way valve in the water, it only allows water to go up towards the pump in that direction. And then we have a priming pot, which is basically a little basket where we can open the lid and fill it with water. Similar to you see attached to a lot of swimming pool pumps. They're built into the pump. Well, what this allows us to do is we open that pump up initially, we fill it with water, and it fills that entire water line all the way down to the sump. But because it has a check valve on the bottom, it won't allow water to flow down past the valve. It stops there, it fills up that water pipe all the way to that water pump, and it floods the line. Then you put the top back on it, and then you plug in your pump. Your pump's already flooded with water, and it begins to flow and circulate normally. So a little something to know, and make sure you're getting what you want, a self-priming or a non-self-priming water pump. You need to look at whether it's going to be a submersible or inline water pump. So if you're doing anything of scale, it's going to be inline. The pump's out of the water, and we plumb into the sump or wherever we're pulling the water from, and we plumb out to where we're going to deliver it. On a smaller backyard home scale operation, it's very common to see a submersible pump, something like a magnetic drive pump, where it actually sits in the bottom of your sump, your low point, and it pulls the water and delivers it to where you need it. We need to look at all of the water pumps available that meet our criteria and choose one based on energy efficiency, expected life, warranty, and reputation. So this is a lot. The water pump is kind of part of the lifeblood of your system. This keeps water flowing. And if you don't have a lot of emergency controls, it can really hurt you if your water pump goes out. So this is a place where you not only want to size the pump right, but then do some research on the companies that you're buying from to make sure that water pump's not going to die a month after you put it in at midnight when you're not expecting it, the worst possible time, and really hurt your operation. Okay, we're going to take a look here. This is a pump flow curve, okay? And it gives us the pump velocity, so the flow rate, sorry, not the velocity, but the flow rate, versus the head pressure. So how high vertically it can pump, okay? Now, a lot of pump manufacturers will only give you a pump curve that has these lines, okay? They're missing this line, and that's the best efficiency curve, okay? This extra little line in the middle here. So a lot of pump manufacturers, you're just gonna see that, okay? And you can size off of that, but if you can get the best efficiency curve, you're going to be able to size it even better. So we see down here, we've got US gallons per minute, 0, 10, 20, 30, 40, all the way up. And then here we've got total dynamic head in feet of water, so up to 35 feet. We're going to do a quick example here. Now in this example, we want to choose the best water pump for the job with a requirement of 90 gallons per minute of flow at 45 feet of total dynamic head pressure, okay? So we go back to this chart and we look at 90 gallons per minute of flow. So we go all the way up our graph here to 90. And then we want to meet it at 45 here, okay? We come out here, come up here, and we're right here, all right? So right at this point, it already tells us anything to the left is not going to work. It doesn't have enough flow rate for our minimum requirement. So we start looking to the right, and right away we see G, pump G right here, okay? It's up here at 45 gallons per minute and 90, all right? Pump G is in the best efficiency curve, so that's great. We look at pump H, okay, at 45 and 90, and it's actually pretty far out, okay? It's a little further away, and it keeps getting further away as we go up in pumps. Now we know a larger pump will of course have the capacity to bring that water, but they're going to be less efficient. So the answer here is pump G. That's the best selection. Pump F, which is to the left, does not have the required flow rate that we need for this specific application. Pump H falls outside of the best efficiency curve and is oversized in comparison to pump G. Okay, we just talked about that. Now, many designers would still choose pump H. Why? Safety factor, okay? If they're off by a little bit, then you can't get a little bit more pump. But you can always turn a valve down a little bit on a water pump and reduce the flow to what you need. So that's just a little bit of professional design insight there, that a lot of people would pick that next size pump up for that factor right there. So we know how to size water pumps, okay? Now we're going to move on to air pumps and blowers. Many types of aeration devices are used in aquaculture and aquaponics, okay? We're not going to talk about every type of aeration device out there. There's paddle wheel aerators, all kinds of stuff that we're not going to use in aquaponics. So I'm just, that's like pond aquaculture, just stuff we're not going to get into. We've got limited time here. So we'll talk about some of the most common types here. And the most commonly used are going to be diaphragm air compressors, linear piston air compressors, regenerative air blowers, and high pressure air blowers for deeper applications. A diaphragm air compressor, okay? So these are used in low to medium volume applications. So usually about 6 cubic feet per minute and under. They're not huge volume pumps. They're used at low to medium depth, so usually 6 feet of water and under. And they work by using a rubber diaphragm, and that rubber diaphragm is moved back and forth via a magnetic shuttle in the middle. Okay, so there's a diaphragm here. Put this clicker down. Diaphragm on each side, and a shuttle is moving back and forth. And as it moves this diaphragm in and pushes this one out. And then it moves back this way and does the opposite motion. And by doing that, it pulls in air and pushes out air. And that's how it delivers the air into the system. Okay? Rubber diaphragms, because they're rubber, they will wear out with heat and with time. So they need to be replaced every 1 to 2 years. The good news, on a several $100 pump, diaphragms are usually about $8, $10. So it's not a big cost on that ongoing maintenance. We have linear piston compressors. Now, linear piston compressors are electrically driven to compress air, building enough pressure to drive the air through the airlines and the delivery device. Low to medium volumes of air, so usually 8 CFM and under, but sometimes you'll see some a little bit larger, of course. Medium to deep depths, so these can pump a lot deeper than the diaphragm compressors because they're pistons. Long-lasting pumps. They typically last, I used to sell these and they'd last 10 to 15 years, sometimes longer, so they were a really good long-lasting pump. The pistons do need to be changed out every 3 to 5 years, but it's not very hard. You could do it in about 10 minutes, and they're much better built than diaphragm pumps. And when we talk about deep depths here, just to go back to that, when I used to size, say, an air pump for lake aeration, something like that, we may have to pump down 50 feet or 75 feet to get to the bottom of a lake and get turnover of that lake volume. Well, you'd have to go with a piston compressor. No way you would ever do that with a blower or a diaphragm compressor. Now we'll move on to regenerative air blowers. So air blowers use high-speed turbine to create large volumes of air at relatively low pressures. And we're talking air in the range of 5 to 1,000 cubic feet per minute. So it can really move a large volume of air, but not to a great depth. These are great for depths up to 4 feet deep, but after that, efficiency drops off very quickly. We can double the pressure out of an air blower by actually using 2 blowers of the same volume and feeding the outlet of the first blower into the inlet of the second blower. This acts as a supercharger, just like in a car, and it allows you to achieve the same volume of air at twice the water depth. High pressure air blowers are also available for deeper applications, but I haven't seen many used, and I don't see many out there when I go out to operations. Okay, so how do we size aeration? Well, this little formula is going to help us out. This is how we calculate the oxygen consumption for the fish. So we take the pounds of fish divided by 100 times A, which is a factor given here, and that's going to equal the oxygen consumption in pounds of oxygen per hour. So here we have A equals, for cold water adults, 0.02 pounds. For warm water adults and cold water juveniles, this is 0.03 pounds. Warm water juveniles, 0.05 pounds. And for bait fish, which are very active, 0.06 pounds. Okay? So calculate the number of diffusers needed. First, we have to obtain the standard oxygen transfer rate, which is the SOTR, from the diffuser description or diffuser manufacturer. So there's a lot of diffusers out there, but we need to know the specifications on that diffuser. Not that it's 3 inches or that it's 10 inches, that it's a square or that it's a circle. We need to know how much oxygen it's actually going to transfer into the water column per given air volume injected into that device. And that's where you won't get any of that from the cheap airstone manufacturers. They just know how to make a square or a circle that looks like an actual engineered product. But when you get down to the specifics, a good manufacturer will have these numbers. The transfer in the stone is a function of the water depth in inches times the pounds of oxygen it transfers per hour divided by 36 inches. So these calculations are done assuming these air stones are placed at 36 inches. But if that depth changes, then the actual rise time for the bubble through the air column or through the water column changes, and other things change, so the numbers change, and that needs to be accounted for. The number of diffusers needed is equal to the oxygen consumption divided by the transfer. Okay, the oxygen consumption of the fish divided by how much those stones are transferring into the water. That gives us the number of diffusers. Okay, hopefully that didn't sound too confusing, but it's really not, so just stick with me here. Aeration sizing. Okay, volume of air needed. Obtain the CFM value from diffuser's description, okay, from where you're buying them, and multiply out how many of those you need. The number of total diffusers times the CFM that the diffusers actually produce is the total air volume. You want to use that volume to select the correct air pump or blower. Okay, so a lot of this comes down to the diffusers you're going to use, what their oxygen transfer efficiency is, and then we get the total amount of diffusers needed, what CFM they put out, and relate that back to the air blower. So here's a quick chart to help you out here, and this is just with a few of the Sweetwater diffusers now made by Bubble Mac. That's who's made them the entire time, but I don't think that Pentair Aquatic Ecosystems actually uses them anymore. So these are for Bubble Mac diffusers that were Sweetwater diffusers for any old-time fish farmers. That was like kind of the industry standard for forever. So here's a few different size stones, AS2, 3, 4, 5, 8, 15, 23, and 30. They don't show their corresponding lengths on here, but I've used these for years. And I can tell you the 30, this is a 1 inch, this is a 9 inch, this is a 6 inch, and then you get smaller up here. And then here you get how many pounds of oxygen per hour they're actually putting into the water, okay, when pumping at this many cubic feet per minute. So here's the airflow. Here's how many pounds of oxygen per hour are moving in. And I always like to use the AS30 for calculations because it's 1 CFM of airflow. And because it's 1 CFM of airflow, that's a nice even number. And then we look back and we relate that to the pounds of oxygen per hour. So we know each one of these diffusers is going to put in 0.038 pounds of oxygen per hour. So what would we do? Let's look at how we would have already come up with our oxygen, right? We calculate that off the feed volume, the amount of fish in that tank, and what the oxygen consumption is going to be. Well, if you're using aeration, once we've calculated our pounds of oxygen per hour, well, right here, we can just divide it by this pounds of oxygen per hour. And that's what we're going to do here in an example. So what volume of air is required for a 4-tank system holding 1,000 pounds of adult tilapia per tank? All right, we'll throw that out there. That's our given. Oxygen per hour per pounds. All right, that is 1,000 pounds of tilapia times 0.03 divided by 100. And that gives us 0.3 pounds of oxygen per hour per tank. If we use the AS30, the 1 CFM stone that I just mentioned we use for calculations, go ahead and use that in this example. So we take the 0.3 pounds and we divide that by the oxygen transfer efficiency of that stone, which is 0.038 pounds of oxygen per hour. And we get 7.89 of these stones needed. And we know each stone is 1 CFM. So 7.89 CFM per tank. And we just size the aeration for 1,000 pounds of tilapia, just like that. 7.89 times 4 tanks, if all 4 tanks have 1,000 pounds in them, then we get a total requirement of 31.6 cubic feet per minute of aeration going into that tank. Now that we have our total air needed, we can design the plumbing scheme, we can calculate the total dynamic head through all the pipes and fittings, and we can select the best blower for the application. So what I like to do is go right from here to picking the best blower, okay? But then that has to do with the pressure. So I picked the best blower just in the ballpark off of this. Then we lay out the piping based on air losses, which we'll go through here in just a minute. And then we can come back to the blowers and see where we need to move. So that's just a personal preference, but you've got the tools to do what you need to do. So sizing blowers is very similar to sizing water pumps. We want to calculate the needed air volume, which we just did. We want to size the pipes. We want to calculate the friction losses through the pipe and the fittings. And then we want to calculate the loss through the air stone itself, because there is pressure forcing through that tight air stone. And then from there, we choose the correct blower. So here's a chart and calculator for estimating friction losses through piping using air, okay? Back to Engineering Toolbox, which is a beautiful site. Here is a chart for estimating friction losses through the actual fittings themselves. Now, air is a lot easier than water because there's a lot less friction loss happening through there than there is using water or a fluid. So there's not many friction losses happening, but we still want to take them into account. So we'll go to an example here on sizing a blower. What is the total friction loss through 100 feet of 2-inch pipe? So for plumbing with 2-inch pipe, 100 feet, and we have 4 90-degree elbows, turns throughout that plumbing schematic. Our volume of air is going to be 99 CFM of air. So first, we need to calculate the equivalent feet of pipe for the fittings. That's the first thing we want to do. So we go to that table that's in the last slide there that has the fitting values. We go ahead and look up what's the fitting value for a 2-inch 90-degree elbow. And from that chart, it's going to tell us that for every fitting, we have 3.3, it's equal to 3.3 feet of piping, of 2-inch piping, okay? So for 4 of these fittings, we have 4 times 3.3, and that equals 13.2 feet of actual pipe, all right? So 4 fittings, 90-degree elbows, 2-inch fittings, they equal the same resistance as 13.2 straight length of pipe, of feet of pipe. Okay, so that's good to know. Now we move on from this. What is the friction loss through 100 feet plus 13.2 feet of pipe? Because that's our total restriction now. 113.2 feet of pipe. We've gotten into a solid singular term. So we refer back to that chart, and it's going to tell us that we have 0.26 psi of loss per 100 feet of pipe at 99 CFM. Right from the chart, it tells us that, okay? So we have 0.26 feet divided by 100 gives us 0.0026 psi of loss per foot of pipe. So we just brought it down to feet. That was per 100. This is per 1 foot. Well, then we take that, 0.0026, and we multiply it by our total feet here, 113.2. And that gives us 0.294 psi of pressure loss through that entire length of pipe and the 4 fittings. Well, 1 psi equals 27 inches of water pressure. It's a conversion factor. So we can turn right from psi into inches of water pressure. 27 inches times 0.294 gives us 7.94 inches of pressure loss. So that's our total pressure loss through the entire straight length of pipe and the 4 fittings. Now, if the diffuser adds another 10 inches of pressure loss, which is very common through a medium pore diffuser, we're going to have a total of 17.94 inches of pressure loss through that entire system, that entire piping system. Now, this can be significant if the blower has a max depth of 48 inches. You might, if you already have almost 18 inches of loss and your max is 48 inches, you might not get the flow that you want out of that blower. So what would we do in this case? Give you a second to think here. All right, well, what we would do, we would increase the size of that 2-inch pipe to 3-inch pipe. You're going to see this 7.94 inches of pressure loss nearly disappear, and you're going to have a lot more workable area, a lot more volume coming out of that blower. The trade-off is that it's more expensive for larger diameter pipe. Plain and simple. This is one more chart that a lot of people might find useful. If you're making your own air stones, which I wouldn't suggest that for any of our diffusion in tanks, but if you're using them in mineralization tanks or other applications where you're going to make more of a large orifice diffuser that moves high volumes of air, check out this chart, because it will actually give you airflow out of the diameter of hole that you drill, which, you know, if you drill a 1/32 inch hole and you have 100 of those, you need to know how much air is going to actually come out so that you can size your aeration device, your blower or whatever you're using. And this chart will allow you to calculate that because they give you the numbers there. I believe there's several charts, but it's near the bottom and it will say airflow orifice chart. And right there again, helpful for determining hole size per volume of air. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.